Okay, so in the previous class, we modeled this physical system of spring and damper as a first order system, if you remember. And here was K, F of T, here was the stiffness K and the C. And we got X of, this is X, output over the input of the system, F of S. Well, we got 1 over tau S plus 1. And if I remember correctly, tau was C over K. Yes? Huh? So having this, we had plus minus the open loop transfer function G of S was 1 over tau S, we put here. And this is the output of the system, X of S over F of S. That's right. And the error signal E. Then, did I calculate the final value theorem for this? No. Huh? We didn't. So, having this, and I plotted this, the response was like this. And I'm going to do that in MATLAB also, hopefully today. Okay. So, X over T. So, the input to the system is impulse. Okay. Here we go. The output to the system that, did I solve it even in the previous class? Yes, I did. So X of T that I solved was 1 over tau E minus T over tau. Meaning that the system is going to be like this. Right? So it means that in steady state phase, the output follows the input. Saying that means the steady state error signal gonna be 0. When time goes to infinity, it means a large value. So we know this from final value theorem, that is S X of, here is Y of F of S. F of S input to the system, 1 plus G of S, open loop transfer function, when S goes to 0. This is the limit of S, because this is impulse, so it is 1, S plus open loop transfer function, not closed loop, open loop transfer function here, 1 over tau S. And this is 0, obviously, when S goes to 0. Okay, everybody? So, being said, when I say the solution is 1 over tau E minus T over tau, what's the role of the tau in the response, guys? So if I increase tau, time constant of this physical system, if I increase tau, okay, it's gonna take more time that this term goes to 0. Everyone agree? Yes? Huh? So it's gonna be like this. Okay? This is for increasing tau. Increasing tau. Also, I'm going to show it in MATLAB. But if I decrease the tau, it's going to take shorter time that this goes to 0. So this is going to be, say, 4 decreasing tau. See, the time constant has meaning. But we know for this system, time constant is the damping coefficient over the stiffness. When we increase tau, we are increasing damping and we are decreasing the stiffness. We are increasing damping coefficient and we are decreasing that. And this is very normal because in your live suspension system, if you have active suspension system, so if you increase the damper and push an impulse from the road like this, suppose this is, oh, what happened? Okay. When it is oh, when you have such a this in the road and this is your car suspension system, suppose that here is a damper and the spring on the tire of your car, so this is can be seen as impulse. I'm pretty sure you have experienced this when you're driving car. There is some train on the road, so you're gonna shock it when you pass it. It's like as a it's a punch to your car. That's right. So this is the impulse to the system. So when you increase the damper and decrease the stiffness, it's gonna take more time that your body settles down to the position that it was. See what I'm saying? Yeah. By the way, your car is second order system. I'll cut from here just giving an example. This is first order system. Understand everyone? Yes? Can you hear me, everybody? Okay. Now, second input that I'm gonna apply f of t for this first, as I told you, is impulse, is step, unity step. Here we go. I'm gonna apply this to the first order system, unity step. Here is 1. Okay, to see what's the response. F of t and t. I want to see how it behaves. And now you know, expert of the Laplace, you know that f of s gonna be how much? Look at the tables I gave you, all of you. What is f of s? Is for the unity step. Yes, here we go. Having that, because you have x of s over f of s was 1 over tau s plus 1, or x of s is f of s 1 tau s plus 1. So x of s is 1 over s 1 over tau s plus 1. Anyone agree? Now you can decompose this from high school is 1 over a in b 1 over tau s plus 1. Okay. The simple way is to do this. A tau s plus 1 plus bs s in tau s plus 1. So if you sort everything, this s with this s, it's gonna be a tau plus b s. Do you see this is equal to 1? That's right. This is equal to 1. This is equal to 1. That's right. So here is 0 because there's no s here. Only is a. See this a equal to 1. Just implementing here, you get b is minus tau. Bingo. So x of s response gonna be 1 over s minus tau s plus 1. You can write it as this, that you can put 1 s 1 plus tau. Yes, everybody? Clear. So what we want to find, we're going to find time response. So what we're going to do here, I taught you, we're going to back from frequency to time domain. What we're going to do? Huh? Yes, Laplace inverse. So here we go. Now you know that what function gives you 1 over s? We just know it. Step. So x of t gonna be unit step minus, and which function gonna give you? Now you know this a million times. What is this? What is this? Please look at your notes. Which function gives you such a Laplace transfer? Which function? Look at the table I gave you. Hello? Guys? Disconnected? Yeah. E minus t over tau. And this is your answer. Clear, everybody? Yes? So, if you are done, I will go to the next page to plot this. Can I? Can I go? So, x of t was unit step minus e t over tau. So, if you want to plot it, this is x versus t. At t0, guys, this is gonna be 1. So your x of t gonna be 0. 1 minus 1. This is your input to the system, guys. 1 input to the system. At t equals to tau, x of t gonna be 1 minus e minus 1. How much was that, guys? I calculated the previous class. E power of minus 1. How much was that? Hold on, because there's a... It's 1.3x. So this is gonna be 0.64. So this happens at where? At time constant. Remember, I told the time constant is the time that the response travels 64% to the final value. So I say as t equal to tau, say here, okay, t equal to tau. So you're gonna have here, say, here is 64.64. See what I'm saying? The time constant you're gonna travel. There's no oscillation here. This is smooth. Okay. Let me delete and replot it. It's gonna go like this. Here we go. Okay, 64%. Then, when time goes to a large value, say infinity, so x of t gonna be 1 minus 0, because when time goes to infinity, this goes to 0. It's gonna be 1. You see that when increase time, this is gonna go to the final value. There we go. For the first order system. So steady state response is here, and the transient response is here. But looking at the steady state response, you easily understand that the error signal is how much? You tell me. Steady state error signal is how much? 0. And we don't need to do that because this is still the first order system that we already calculated, right? Nothing changed. Only what? Input changed. So input is now a step. So here we're gonna put 1 over s. 1 plus 1 over tau s. When s goes to 0. This with this goes to New York. So you have 1 over tau s plus 1 over tau s. So you can write this as a limit of tau s in tau s plus 1 when s goes to 0. When s goes to 0. It's going to be 0 because this is 0. Clear? Yes, everybody? Before continuing to, guys, oh, sorry, when you are done, let me know. So before continuing to third input, that is ramp, I want to take you to the MATLAB and simulate there. So guys, we said that output over input of the first order system in general statement is 1 over tau s plus 1. Okay. I told you that in transfer function frequency domain, you have the numerator and denominator, that's right. So, on the other hand, you have one pole here. What's the pole of the system? Pole of the system that we are showing with P, pole of the system is 1 over minus 1 over tau. If you plot this in the complex plane, imaginary and the real. So your pole that we're going to show with the cross is the left hand side and is real values, right? And I taught you in the beginning of the semester or mid of that. So whatever is inside the left hand side saying your system is stable and we are not blind. You see that system is stable and converge to the input. Or here. System is stable, converge to the input of the system. So here is stable. That's right. Here is unstable, as I told you. If you have any real or imaginary poles of the system, your system is unstable. And whatever is located here is what? I name it what? I named, yes, marginally stable. Okay, so you see that your system is stable. But we don't have any zeros because it's a constant number. So on the other hand, this can be written as this. Look at here. 0s plus 1. That's right. Tau s plus 1. That's right. And the system is first order system. We are still there, not in the second order system, physical systems. So this is how we define in MATLAB. We say numerator is coefficient of the highest value s is 0 and 1. Here we go. Okay. Then for denominator, then it's tau and 1. See? From highest order to lowest order. And you can extend this for the third order system, fourth order system, nth order system. Okay. Then to plot the step input, as we did here in MATLAB, here, you're going to say this command, step num, and then, here we go. Simple like that. I'm going to back this here because I'm going to talk about the impulse. Okay. Now let's go to the MATLAB. Can I? So, and the Simulink, obviously. MATLAB. Low. Oh. There we go. Okay. I'm gonna open also share with you the file. I'm gonna open file. Okay. I'm gonna say tau 1 is 2 seconds, 2 tau 2, because I'm gonna plot different remember that I'm increasing the time constant of the system. Okay. And then I'm defining num equals to 0 and 1 for the first order system, then 1, because I have two systems for this, gonna be 1 2 and 1. Oh, sorry, let me write like this. Tau 1 and 1, and then 2, because numerator is the same, is tau 2 and 1. See here, tau 1, but I'm plotting to examine this. To examine what, guys? To examine when I say oh yes, when you increase tau, when you decrease tau. So I'm saying here is 2, here is 4 tau. Okay, I just want to plot it. Then I'm saying step num and then, okay, then 1. Okay, and hold down because I want to plot at the same thing. So step num and then 2. I'm going to save this in your file. Okay, to step impulse plot, because I'm going to share it with you. Okay, so if I plot this, it's going to take a while. See, it's computing here. Here we go. Do you see, guys? This blue line is for time constant of 2 seconds. This red line is for time constant of 5 seconds. Simple like that. You see, if I increase the time constant, it takes more time to settle down. Because I'm going to put it at 10, for God's sake. And let me also, I say, clear close all means close all the figures. Okay, here we go. See, now we have huge difference. When I set to time constant to 10 seconds, it takes much more time. See, 60 seconds. See what I'm saying? Yes? Understand? For saying the legend, the first one is tau 1, and the first is tau 2. There we go, hopefully it plots. Yeah, here we go. Tau 1 and tau 2. Okay, here we go. I can put the numbers. Tau 1 is 2 and tau 2 is 10. There we go. Okay, understand everyone? Yes? Hello? Can you hear me? Hello?
Yeah.
Okay. So you can grid it. And, okay guys, one of the things that you have to know. When I plot this, you see that we have extra time here after here. That's why I don't need it, because it already settled down at until 70 seconds right here. So you can cut it out. How? You can say put time from 0 to 70. Here you can say time to have a better graph. Here we go. See that? I cut it from here. Okay? So this is how you plot the step response. Even automatically, MATLAB knows this. We said the step response. Amplitude, time. You don't need to do anything about the axes. Clear? So, but you're gonna tell me, okay, let's try payment. In figure 2, I try impulse now and then. 1. Because I want to also see the impulse. Because we plotted this. So let's try together, huh? Obviously, it's going to give error because the MATLAB has no impulse command. See? Cannot understand the impulse. MATLAB has only step. So there's a trick, guys. So let me go back to the notes. So the trick is this. Okay, guys. Look at here. X over F is 1 tau S plus 1. Okay. Guys, can I write like this? All of you look at here. X over S multiplied by 1 over S. What is this, guys? You tell me. You let me know. How much is this finally? How much is this? Can't you multiply S by 1 over S? Guys, you don't know this from high school? How much is this? Yes. Now, what is this? I just taught you. Laplace of what? Laplace of what? What? Step. So, You are saying, you know what? I'm gonna have the step as input. Bingo. And I'm gonna move S to the other side. See? I'm gonna move S here. Gonna be S in tau S plus 1. Interesting, right? Because Laplace of impulse is 1. So we created 1. Here we go. That's right. Laplace of impulse is 1. We created 1. But I'm moving the S to the other side. Only I'm keeping 1 over S here. So this is gonna be the formatted transfer function still under what? Under step, but gonna show you the impulse response because originally it was like this. This is impulse response. See what I'm saying? Yes or no? Huh? Good. This is just my sleeping hand. Okay. So now you have to change the numerator for the impulse. So num gonna be, because you have, by doing this, I change the transfer function. Not only you have the poles, now you have what I told you. What's the name of this? What the name of this I told you? Zeros. That's right. So zeros that we are showing with the z, this is the pole. If you solve this, gonna be 0. So we are changing the system transfer function. We have it, and we are showing with the circle in control on this course by this circle. So at 0 we have 0. So your num gonna be 1, 0, and then is the same as before. Tau on 1. See? We change now. Clear, everybody? Yep. So I'm gonna do in MATLAB. So I'm gonna say I have to change it. I have to say num new gonna be 1 and 0, but we don't need to change the dens because dens are the same. See what I'm saying? So figure 2 is again step num new then 1. See what I'm saying? And hold on, because we're gonna see the effect of the time constant on the impulse response. Step num new then 2. And I'm doing the grid legend to make it more interesting. Okay? So that's it. If I run this, it must show the impulse. Oh yes, it shows. See? Do you see it? So tau 2 is 10. It takes more time to settle down, and tau 1 is 2. This is impulse. Psh, exactly what I plotted here. See, guys. Here we go. And I told you because it's too much, you can cut out at 50. I'm gonna say time for new is 0.1250. So here you're gonna put time new for the impulse. I'm gonna share with you this code. Okay, here we go. There you go. It's more visible now. You see, the both cases, it doesn't matter that what are it shows the step response, but it's not because we use the step command, but this is impulse response. Actually, you can change this. Okay, you can change this. How you can change this, if I remember it, you can say title impulse response. Here we go. I changed impulse response here. Okay, title of the figure. And obviously, I'm gonna do, because I'm gonna share with you, I'm gonna align width for all of them must be 2 to give you more I'm not sure this works here. Let me first try. No, it works on the step. It doesn't work. Forget about this. I forgot it. Okay. So here we go. So we did this. I'm gonna extend this to next class. But what I wanted to show you here is this, guys. I'm gonna plot this exactly in the Simulink and get the same response for the step. Do you see this? So I'm gonna go to home. I'm gonna send this to you, this file, and I'm going to Simulink. Here we go. Okay. I'm saying blank model. Okay. Gonna wait until it comes up. Come on. Let me pause this to save time. It's gonna jump, just leave it. Okay, it's creating the model. Hello? Okay. So when we have this, I'm gonna make it bigger. You're gonna push this library browser. So I'm gonna do that. Yeah, obviously. Okay. So I'm gonna plot this there. We're gonna put is step, then search this. Okay, search this. This is a step function, guys. I'm just dragging and putting here. Simple like that. Just give time. Here we go. Then I'm gonna say transfer function. Give time. Okay. Transfer function. I'm dragging and putting here. Then I'm gonna need sum minus. Remember sum operator? Sum. I'm just putting sum. Okay. So here we go. Sum. Exactly that I plotted here. See here, guys. Here we go. This. Then you wanna plot it. That's right. You're gonna say scope. Scope. Here we go. I'm gonna plot it. Now this is unity feedback. Let me move all of them to the middle of the screen. I'm gonna share also this with you. Don't worry. So this is unity feedback. I'm gonna make as we did here. So see. So here we go. This I'm connecting this to this, this to this, this to this. Then you come here, right click and holding right click. Okay, and then as you doing that, you're gonna connect this to this. Now this is unity feedback block diagram. Understand, everyone? Right click, hold it, and then do this. But as you see here, here is plus minus because we're gonna get the error signal. So double click on this. You see it shows plus plus. You change it to plus minus. Apply. Here we go. Now it's just plus minus. Understand? Then double click on the step. It says step time is starting at 1 second. No, because it's gonna be delayed. See, what it says is this, guys. It says, I'm gonna apply like this. Oh, it's a delay, 1 second. We're gonna start at 0. So this is 0. Yes, initial value is 0, final value is 1. Yeah, exactly. This is unit step, remember? So apply, okay. Now let's go to our transfer function. Our transfer function for the first order system was for not impulse for the step is 0, 1, 2, 1. For example, that we have 0, 1, 2, 1. So you can keep it here 1, but it's better that you put here 0, 1 as you typed. The numerator coefficient, denominator coefficient, and 2 and 1. Is this correct, guys? Is this correct I'm doing in the denominator? Is this correct that I put this here? The whole of this? Guys, look at here. I told you what you're gonna put here. What you're gonna put here? What's the name of this? What is the name of this? What's the name of this, guys? What? Or here was closed loop transfer function. Yes? Yes, so you are not allowed to put 1 over tau s plus 1. You have to put 1 over tau s. See what I'm saying? Yes? In the code, let me show you. In the code, you have to put the closed loop transfer function. But when you come to Simulink, that's the difference between coding and Simulink. You have to put the open loop transfer function. So you're gonna put tau and 0. It's because it's gonna be 1 over tau s. Look at here, guys. Do you see it? Yes, everybody? Now this is open loop transfer function, 1 over tau s. Your tau is 2. Understand? I'm double emphasizing a million times. In the Simulink, put the open loop transfer because this is unity feedback control loop. Yeah, like at the code that we had here, remember? I'm gonna share both. See? 2, tau 1. So I'm gonna put 10 also. Doesn't matter. So then I have to save it. Let me go to this. I'm gonna say Simulink step response. And the file is being saved is the MDL files. MATLAB coding is M file, but this is MDL files. Look at here. See? This is Simulink. Actually, now they changed it to SLX file. Okay, previously was MDL files. MATLAB is updating. Okay, so now it gives you stop time. It means that I want to run it for 10 seconds. Okay, but okay, now you can change it to 20, you can change it to 5, whatever. But default is Simulink is 10 seconds. Okay, so now I can run it. Push the run button. See, it's compiling. Now you can double click on this. on the scope. Here we go. Step response goes to the 1. See it? Step response. Here we go. Simple like that. Understand? Yes, guys? And obviously, you can click on this, all Control C, Control V, copy and paste. Works here. Okay? Then you can plot, because this is error signal. If I double click on this, you see the cursor comes here. You can see E of S. You can label the signals here. Means the error signal. Then, as I told you, you can right click, hold it, and put it here. Now you can plot also the error signal, because I promise you by mathematics error signal goes to 0. So let's run it and see it. Here we go. You see, error signal goes to eventually 0. If I increase time to 15 seconds, there we go. Yeah, goes to 0. Exactly goes to 0. Error signal. As your response converges to the input, which is impulse, which is step. See, exactly to the 1. Do you see that? Yes. Now I'm copying and pasting everything here. Putting here. You're gonna tell me why. Because I just want to. Oh, Control Z works here. Means go back. So I'm gonna do this, guys. As your friend asked, I'm changing the time constant to 10 to compare the responses, as we did in the MATLAB code. 10. Okay, here we go. Then you can cut from here and put the both here. Double click on the scope. Okay. Then you can say max, search for max. Okay, this is the max, taking 2 inputs, giving 1 output. Here we go. But the max, you can change the number of the inputs. Because here is 2, you can say 5. See what happens? 5 inputs, but we need only 2 here. Okay, 2. So what I'm gonna do, I'm gonna plot this here. Again, I'm gonna put right click and this here. Then I'm gonna plot both together. The same, I'm gonna put a max for error signals. See? Copy and paste. Oh. And then move it here. See? Right click. Here we go. Right click. Here we go. Now save it. Okay? You see, with different time constant. If I run it, here we go. This is when the tau is 10. That's right. You have to increase time to see everything. So I'm gonna say to 70 seconds, if I remember from the previous example. Okay, and now run it. Here we go. So you can compare the responses and the sibling at the same time. This is for tau 10, this blue line, and this is for tau 2, as we did in encoding. The same valid for the error signals. Tau 10, tau 2, yellow line. Clear, guys? Now I want you to use the trick, this trick that I taught you, this, and implement here, guys. See if it works. This is just homework I'm assigning to you. And don't forget, here you have to put open loop transfer function. See that the tricks I taught you works, and this gives you, these blocks give you the impulse response as we did in the coding. Here we go, as we did in this coding. Okay. Any questions? Or even that, let me teach you this. I'm gonna say 3. Why? Because I'm gonna say compare the real output, but one of the inputs, which is a step. That's right. See? So if I now run it, see guys, this is the input, this orange. That's right. Input is 1 unit step. Is being conversion. So I'm gonna share all of them to you. So let me first